Ladies and gentlemen, the Science Symposium is about to begin. Thanks to the support of many parties, the Future Science Prize Week has been a great success. Please give a big round of applause to show your appreciation. Organizer, the Future Science Prize, and co-organizer, the Hong Kong Academy of Sciences. Our strategic partners are Sino Group, Shangri-La Group, Tencent SSV Organization, the University of Hong Kong, the Hong Kong University of Science and Technology. Our partners include Qiming Venture Partners, 5Y Capital, Sanofi, Future Innovation Fund, Fully Supporter, Leisure and Cultural Services Department, and our supporters including Hong Kong Science Museum, Hong Kong Space Museum, the Hong Kong Young Academy of Sciences, Hong Kong Subsidized Secondary Schools Council, Hong Kong Direct Subsidy Scheme Schools Council, Association of Principals of Government Secondary Schools, Acknowledgement, including All Stars Investment, CTF Education Group, Lenovo, TrustStar Capital, WeLight Capital, Alcoholic Capital, Cowlick Consulting, Frontier Foundation, UBS, 1886 Holding Group, Tomakado, Computing Art Lab, and our media partner, Radio Television Hong Kong, RTHK, our funding organization, Innovation and Technology Commission. Without your support, the event would not be so successful. Thank you very much. Distinguished guests, ladies and gentlemen, parents and students, thank you for joining the 2024 Future Science Prize Week and the Science Symposium. It is my great pleasure to be the MC today. I'm Yo Yilang. Hello, everyone. Good morning. Good morning. We are so thrilled to be here with many great minds of the year. The Future Science Prize Week aims to promote scientific spirit and pay tribute to scientists, leading the public to explore the forefront of world science with a forward-looking perspective. This year, our program committee sets the agenda and invites domestic and international keynote speakers to ensure the high level of academic content and extensive global perspective of the conference. The next session will be physics session, quantum information. To begin with, program committee co-chair and the convener of physics session, Professor Douglas Nelson Cholin will deliver welcome remarks and introduction about the physics session. Let me introduce his profile. He is Professor, Astronomy and Astrophysics, University of California, Santa Cruz. Distinguished Visiting Professor, Institute for Advanced Studies, Tsinghua University. Member, American Academy of Arts and Science. Member, Science Committee of the Future Science Prize. Co-chair, Program Committee of the Future Science Prize Week 2024. Let's welcome Professor Lin.
Thank you. Distinguished guests, ladies and gentlemen, good morning. It is my honor to be the conveyor of this morning's section on quantum information. This subject is one of the most fascinating and enigmatic areas of scientific endeavor. We are fortunate to have preeminent pioneers as well as rapidly rising stars from Europe, US, and China to share their contributions and perspectives in this rapidly advancing branch of physics. Let me introduce each of the speakers. First, let me introduce you, Professor Peter Zoller. Professor Zoller is an internationally renowned theoretical physicist whose main research area includes quantum optics, quantum computing, quantum information, and quantum simulations, basically quantum everything. Professor Zoller is well known for his pioneering work in the field of quantum computing, particularly for his theoretical proposal with Ignacio Cirac on using ion trap systems to implement quantum entanglement gates. This theory laid the foundation for quantum computing to transition to experiments and inspired the discovery and the development of other physical platforms with the potential to achieve large-scale universal quantum computing. Professor Zoller's research accomplishments are not only theoretically significant, but also have inspired a wide range of experimental physics programs. His work has built a bridge between quantum optics, quantum information, quantum metrology, and promoting the development of quantum communication and quantum computing technology. In addition, Professor Zoller has explored large-scale entanglements in quantum simulation, developed new measurement tools that can study physical phenomena previously unattainable, and helped better understanding of quantum materials. Professor Zoller has received several international awards, including the World Prize in Physics, in recognition of his outstanding contribution to the field of quantum computing and quantum information. The title of his lecture is Quantum Simulation with Atoms and Ions. Professor Zoller, thank you.
Okay, so let me first of all thank for the invitation to come here. I really feel honored to be part of this Future Prize Week here. And this is a session here on quantum information. Since I'm the first one, what I would like to do is sort of, first of all, give a very general introduction that's maybe more aimed to high school students or undergraduates, and then sort of move on to the second part of my talk, which is sort of what we're doing right now, which is quantum simulation of lattice gauge theories. We have some new results along these lines. At one point, this gets a little bit more technical, and we'll try to talk about it, of course, in very qualitative terms to give you the whole spectrum, what the ideas, then all the way forward to sort of new results. You might ask yourself, what this picture is. This is a painting in the entrance hall of our Quantum Institute, and this is Erwin Schrödinger, one of the founding fathers of quantum physics. He wrote down the Schrödinger equation, that explains atomic physics, quantum chemistry, nuclear physics, and so on. But he's also famous for the Schrödinger cat down here. These are these cats that are dead and alive at the same time, and probably you have not seen so many of them walking on the street, but you will see them today because they live in our quantum computers. Of course, not as real cats, but they live in our quantum computers as superpositions of zeros and ones, what we call then entangled states of a quantum register. This is a title of my talk here. I will talk a little bit about quantum computing and then in particular about quantum simulation. My own background is atomic physics, and so we are going to speak about quantum processors and simulators, mainly built with atoms and ions that we would like to control then with laser. This is a long story in the meantime, because we are celebrating actually this year the 30th birthday of quantum information. Peter Shor wrote down the Shor algorithm 30 years ago. This motivated a lot of this work and our ideas regarding ions and so on that I will explain now briefly, also now 30 years old. Let me start out by simply telling you this is sort of an old-fashioned ion trap. It's like, when you have an old car, you can still raise the hood and look inside. There was the real engine inside. very similar here. This is an ion trap, and you can see the individual ions. So very often people are impressed to say, oh, you're storing information in single ions, in single atoms. That's quite impressive, but of course, this is not the point of the story. The point of the story is that this is single atoms that we prepare in vacuum in free space, and we trap them with electromagnetic fields, and they are charged particles. They repel each other. They form a little crystal that you can see over here. But they have also internal structure like spin. And this at the end will be our qubit that we are going to explain now later. And of course, this is basically what at the end will correspond to the Schrödinger cat that we just talked about. The point, of course, is that this quantum computing should not be seen as an extension of sort of the standard classical computing being fast or whatever in any way, but really as a new paradigm. A new paradigm that I guess will really shape our present century that we have in providing really new information technologies, and I think that we are really well on the way of actually achieving that. Of course, talking about these ions, there's a question of we have to scale up these quantum computers. And, just in the case of the ions, you can make 2D crystals, very long 1D chains. And, what used to be sort of labs like you saw over here, the big picture, on the right upper side over here, you can see that, this is sort of all of these things now put into a rack. So we are at the point where these things get condensed in racks and are sort of useful as computers that you can really install also in computer centers. But for those of you that are sort of maybe not so familiar with quantum information per se, talking now to the undergraduates and maybe also the few high school students that are here, let me explain a few of the basics. When we talk about classical bits, they can be either 0 or 1, and a quantum bit can be in what we call a superposition of 0 and 1. So it's sort of 0 and 1 at the same time. And we always have ways of representing it by something that we call the Bloch sphere. Classically, there's only the South Pole and then the North Pole over here. But quantum mechanically, it's like visualizing this thing that all points of the sphere are possible states if you're a quantum state, representing the superposition of zeros and one that we can store in our quantum register. And this is an attempt, sort of a classical attempt to represent these things. Depending how you look at this picture, it's either an old woman or a young woman. Of course, we can take our classical bits and our quantum bits and we can combine them to what we call either classical registers by having like over here 0, 1, and 0, but also then a quantum register where we have now superpositions of all of these numbers that are at the same time live in our quantum computer in this quantum memory that we have. And of course, at that point, what we have is exactly the Schrödinger cats that we talked about now before as the superpositions of zeros and ones that we are storing in our quantum computer and which at the end then give the whole thing the power of quantum computing. Of course, the space where all of these things is happening is actually huge. So when you take something like 300 of these qubits, you got 2 to the power 300 states, and they are represented simultaneously in your quantum machine. So in this sense, you can see that we have a huge space over here. This Hilbert space is really huge, and this is what made Feynman say, of course, that suppose that you would like to do computations on a classical computer of, say, quantum materials, it becomes at the end very hard, but this entanglement here gets very, very large. Let's now have a look inside what we have to do in order to understand and at the end and also build a quantum processor. What is the task that we have to do? So we have here input states, down here that are the different qubits that are entangled. And of course, we have to operate on these qubits by what we call quantum gates. So these are operations on the qubits here that either can be so-called single qubit operations or then entangling operation down here. At the end, the question is, how do we do that in the real experiment? And, the single qubit operations basically correspond to a rotation on this sphere that we talked about before. We call it the Bloch sphere, or there can be something like a Hadamard gate over here. But we can also, and this is sort of the tough part in designing a quantum computer, think about how to make what you call 2-qubit quantum gates, where one is the control and the other one is the target. So depending if the control is on the South Pole or the North Pole, 0 or 1, you can either do nothing or you can maybe swap the two states on the other qubit that you have over there. Implementing, of course, these entanglement operations is the core and also the main difficulty in building a quantum computer, apart, of course, from the fact that you have to isolate your Schrödinger cats really well from an environment. You can see here that these kind of gates act on superposition states. So in this sense, we have in our quantum computer not only a single number, but a superposition of different numbers, and we act with these gates in parallel on all of them, and this is what we call here quantum parallel processing. Let me now go back to the ions, and as I said before, this is a string of single charged particles that we have laser cooled down to very low temperatures. We trap them in a vacuum in the chamber, and we want to convince now this object here to act as a quantum computer. And of course, for us as physicists that know a little bit of atomic physics, we know that these are atoms that have maybe, say, an outer shell electron, and this outer shell electron can have a spin, and this spin can act as our qubit. It can be spin up, can be spin down, but of course, any superposition state, and if you got the whole register over here, it can also be entangled. This is quantum memory, and it turns out that the quantum memory of these atoms in terms of quality is really, really high. This quantum memory has a lifetime of, well, depending how they do that, in some cases and can go up to maybe even minutes. The internal atomic physics that's going on is that you have here, for example, in these calcium ions, very long-lived states, that live, in this case, a second, and in particular realization over here. And then we have here other lasers that allow us to read out the qubit here in terms of measurements. But the central part, of course, is how to do gates. And the single qubit gates are very simple because we only have to shine lasers on the individual ions to rotate them, and this is not very hard, but of course technically challenging, but conceptually quite obvious. The question is, how do we get the entanglement? And the entanglement, in the case, the ideas that we had together with Ignacio Cirac were that these ions, they also have motion, they vibrate, as you could see over here. This is, of course, classical motion, but we can use this motion, if you cool it down to 0 temperature, also as a data bus to communicate, qubits from one internal state to another internal state of some other ion. And this, at the end, allows us to design quantum gates, and they have been implemented now in experiments, up to the point where we have sort of a whole library of different operations on these strings over here, acting with our lasers. We can read them out. And we can easily perform now, without doing any error corrections, for example, a few hundred of these quantum gates at the moment until the whole thing falls apart. Of course, we would like to do that with an increasing number of particles here. And just to sort of tell you where one is at the moment, I've taken as an example here, that's H2 Quantinuum computer, that you can actually buy. And if you look at the gate fidelities over here, you can see at the very beginning, when people did the first experiments, they had gate fidelity, which is the quality of these quantum gates of about 85%, maybe 90%. In the meantime, there's a lot of 9 over here. This means that these gates that we are talking about can be implemented in the experiment with very, very high fidelity. And this, of course, is a good starting point. This means that error correction is something that, is either maybe not necessary in some cases, and in other cases, has to be done only very infrequently. So in this sense, we have gone a very long way from initial ideas, 30 years ago, first experiments on single ions, and now they talk about actually in some of these cases, even a few hundred ions where they do this kind of a quantum computing. But let's take a step back and simply say, of course, I've given you the example of the trapped ion quantum computing as as a historical first example, but as an example that also survived. We have, of course, now several other examples out there, from, for example, in particular here, superconducting qubits. We have then, for example, defects in solids and so on, various solid-state devices. This is trapped ions over here, and atoms and so on. I'll talk afterwards also about Württemberg arrays, which is now, I would say, one of the most promising systems in terms of scalability, but I'll come back to these things later. But if you want to summarize, we can really say here the key features are, or the requirement is that in developing all of these things, first of all, controllability. You would like to be able to control down to the level of a single quantum, a many-body system with a growing number of qubits. So this scalability, this controllability is key. And at the same time, of course, you have to do that in a way that this controllability is preserved by scaling up the number of qubits to a very, very large number. And this is sort of the fundamental rivalry that we have in building these systems. And this is, a slide that I've copied here from actually Misha Lukin, who gave it to me. This is the guideline, I would say, for what's going on at present, that we have different platforms, but the controllability and scalability, of course, are the key features that we have to try to implement in these experiments. So the current frontier, if you want to read this, is that you would like to do here tasks, that they are beyond maybe the classical computing that we can do at the moment. And we want to do that, now with qubits that are approaching now, I would say 1,000. And I would say that some of these systems obviously scale to higher numbers. We want to test and implement useful algorithms and applications. And of course, at the end, we also want to do error correction. And I would say that many of these things have now been achieved. And just in the last year, in terms of error correction, I would say has been a highlight, in the development of all of this and the application of these quantum machines. Let me comment just, and then I move on to this quantum simulation part. Let me just comment on briefly, where the power of quantum computing actually comes from. We have talked before about, having a quantum register and superposition states over here. If you think about a classical interferometer over here, then you can see that an interferometer has two light beams that eventually interfere to constructive interference, or maybe destructive interference, giving rise to interference fringes. And in a quantum computer, something is happening, but on a sort of a much larger scale, because you got this huge Hilbert space over here, the huge Hilbert space that represents the Schrödinger cats over here, where you're doing sort of in parallel all these different computations, which at the end can interfere, giving rise to algorithms. And I just want to point out again that Peter Shor came up, of course, with the factoring algorithm now 30 years ago. Somehow this was the initial point and also the motivation to develop many of these things. But of course, in the meantime, we have many other examples also. But one that I find particularly interesting is the problem of solving quantum many-body problems, which is what we call the problem of quantum simulation. So I would like to switch over now to problems that I'm personally also very interested in, because they really are physics problems in nature where we are trying to solve from quantum computer, either digital or analog. I will give you analog examples now in the following, many-body problems. And this goes back, of course, to Feynman's original vision, who said that classical computers have difficulty simulating this many-body problem because of entanglement, and now we learn how to control entanglement in a programmable quantum machine in order to do that. And we have, of course, many examples, and you should see this like constructing a special purpose quantum computer here, where we might design different kind of materials, maybe design also quantum chemistry, different drugs and molecules, but of course, maybe also do very fundamental science, like, for example, doing here, I don't know, high energy physics and being able to do simulations that are beyond what one is able to do right now. And they will afterwards show you sort of a little toy model that tries to go in this direction over here. Let me first remind you, however, briefly, why sort of in our condensed matter language, this simulation is sort of hard. Classically, if you think about, this is a magnetic drive that some of the older generation might still remember. Basically, think about it as having many spins that are in a certain configuration. It can be spin up, spin down, or many other configurations. Quantum mechanically, of course, we have all of these 2 to the power n configurations simultaneously. And this is sort of the power why we would like to do quantum simulation, that we're able to handle these large superpositions, in our quantum machine in a controlled way. And this, of course, is just, as I said, Feynman's original idea how to do all of that. Let me now switch over to a little bit more technical part, but I would like to make it nonetheless very qualitative by trying to explain to you some of the physics that we are trying to do over here with my hands rather than in writing big formulas. But at the end of this thing, there will be an experiment that will allow us or sort of show us in this context what one is able to do at the moment and where, in terms of science applications, some of these developments also go. So lattice gauge theories, of course, appear. Quantum chromodynamics is one example in high-energy physics. And I've taken here two examples. On the left-hand side, you can see that we have here some phase diagram where we have different states of quarks bound together, or maybe moving freely, like a quark and gluon plasma and so on. And on the fundamental level, this kind of interaction between these particles is described by gauge theories, or if you put them on the lattice for computational purpose, by what we call a lattice gauge theory. And these kind of different phenomena on the left-hand side, you can see over here these quarks bind together to nuclei. This is the nuclear physics over here. Over here we have something like color superconductors and all of that. Can we understand this phase diagram? And of course, on the high-energy physics side, fantastic methods have been developed to describe and compute these phase diagrams, except, of course, that one has difficulty in going to the very high density limit over here, because then classical Monte Carlo simulations fail. And of course, there's another range of experiments which are really collider experiments, where we have all of these jets that go out to describe or sort of model from a theoretical point of view these kind of processes is something that is really, I would say, on the large scale impossible. And one can do, of course, many approximations like semi-classical and so on. But this is where maybe quantum computing can find its own purpose and its own niche here. And so we have here the computational sign problem, either in real-time dynamics or at finite baryon density. And this is, of course, also something that we have in parallel, not only in high-energy physics, but there's, of course, counterparts also in condensed matter physics and more general, and also in the more global context in this quantum information context. So let's think a little bit about what these kind of things are, to what extent we can develop and program our quantum machines to handle these things. I have to tell you right away that what you can see on this slide is something that really goes beyond what we are able to do at the moment. This is far too big for the machines that we have right in the lab. But what we can try to do is to identify certain phenomena that we identify as being important. And this will be string breaking now in the following as one example, that we have confinement, deconfinement, that we see confined phases and the corresponding properties and all of that. And to construct very simple toy models that illustrate certain phenomena, knowing, of course, that we are pretty far away from this ultimate goal that we would like to do over here. But it is amazing to see that the machines that we build at the moment are able to provide us with quantum simulations on the level of these toy models. And this is what I would like to talk about now in the following. So the phenomenon that I would like to speak about and to show you then experiments and afterwards is the phenomenon of what we call string breaking. And string breaking basically consists of, well, let me simply explain it like this. Imagine you got some rubber band and you pull it more and more and more. At one point it will break, And very similar, if I take, for example, a classical charge, positive, and the other one negative, and I got now an electric field, line connecting these things, an electric flux line connecting that. If I make it longer and longer, there will be more and more energy stored, electric energy stored in this string. And of course, at one point, it will be for the system easier or sort of simpler to produce pairs of particles created from the vacuum, electrons and positrons in the case of quantum electrodynamics, that will break the string. And this is what we try to indicate over here. This is a picture I've copied from the internet, that we have here these two charges. We pull them apart, and at one point you create here electron-positron pairs, or maybe quark, anti-quark pairs, and so on. And this is the phenomenon of confinement that we have, and is fundamental, of course, in all of this quantum chromodynamics, but of course also in the context of electrodynamics we have that. So if I get a little bit more quantitative, you can see that we have here two things in our context. On one hand, we have here the potential that corresponds to a certain length n with a string tension. So the longer the string is, the more energy you store in here. This is the line that goes up here. And you can see that we also have here a broken string, where, of course, this whole thing has collapsed to just here two, let's call it mesons. This is a meson, and this is a meson over here. So this is a quark and antiquark over here bound here to this charge that we have in our problem, where the energy has been now become independent of this distance d by forming now this, in the sense of pair production, two particles over here that are now bound, and now you can see this corresponds to the line up here. So the ground state of the system will be, well, the string gets more and more dense, then it breaks, and then it will be flat over here. We'll try to see these things in the following, then in an experiment where we design a lattice gauge theory, and if I, just in a very elementary way, try to represent this kind of physics and a lattice gauge theory, then we would have here, a lattice where each side carries matter, and we put here classical charges, the red one over here and the other one over here. And now you can see here the corresponding electric flux line, for example, connecting these two, and the broken string now corresponds to having created an electron-positron pair, a quark, anti-quark from the vacuum, that now form these bound mesons. So this is sort of on this toy level, a kind of dynamics, and that we would like to describe and now try to see and model in our experiments. Can we identify systems that do all of that? And we just put a paper on the archive, actually, now a week ago, which was an interesting collaboration for us between Innsbruck Theory and Quera. This is a startup, starting from Misha Lukin's group at Harvard. Misha Lukin is also here, where we use their machine in order, this machine is called Aquila, has 256 qubits, in order to simulate here, in a sense of creating synthetic quantum matter, that shows the string breaking, and where we have tunable parameters that show all of these phenomena that are sort of fundamental on this level over here. And quite interesting, in more or less within 2 weeks, two more papers appeared. One from Google, they did digital quantum simulation of the same problem. You can see a 2+1D lattice gauge theory, and then there was a 1D experiment coming from the Chris Monroe group at Duke University in collaboration with Maryland. So I talk about the experiment down there because this is the one that we were involved and tried to do now for 2 years and made a lot of progress then just during the last few months. And I would like to give you a qualitative idea what can be achieved and what can be done in these kind of toy model simulations of lattice gauge theories. But before I do that, let me tell you a little bit about Rydberg tweezer arrays, because this is the hardware which underlies all of that. And very similar to the ions, I worked on some of these things now more than 20 years ago, and now they are finding their realization in the lab. And of course, what the experimentalists do here is this. They would like to build quantum systems one by one, and I find this a very amazing story, and just show you a few beautiful pictures that I've collected from my experimental friends, in particular from actually Misha Lukin at Harvard. And this reminds you that when we talk about tweezers in biology, we have light, which allows us to trap and move, for example, small dielectric particles around. We now would like to do the same thing with single atoms. We can catch single atoms and trap them in a tweezer, which is a focused laser light, and we can do that for many. And we are trying to catch these atoms. Of course, we might not always be successful, but we can look if you see these atoms, if they are trapped or not, and you delete the ones which have no particle, but you can rearrange, because these are tweezers that can be moved freely into any configuration that you want. And I always like to show this example down here. This is a 1D example. You tell them any pattern that you want, and at the end they even write your name, but this costs you a beer, I have to tell you, and so it doesn't come for free. At that point, you might ask, what's the distance between these tweezers? About, say, 10 micrometer, very similar to the ions. And the question is how to make interactions. And I would like to tell you now a little bit about how this is done, showing you a few beautiful pictures, but then we get serious and we go to the experiment and try to simulate the lattice gauge theory. Of course, what I show you, this free arrangement, is not only 1D, could also be done in 3D. This is from France. Antoine Brouet's group has done these things. And the question, of course, how to make the atom interact. And I have a few pictures here on this Rydberg electrons. I find them quite entertaining. So let me show you. So if you got an atom, of course, we have think about Bohr radii at the moment, or Bohr orbits. We have different Bohr orbits here. We can, of course, take one of the ground states of these atoms, and we can excite them with lasers to very high Rydberg states, with the quantum number n, which is really large. And there's, of course, this famous Rydberg formula, which was the starting point of our atomic physics. And if you look at the numbers here, these atoms, by bringing them to Rydberg states, you make them huge. They become roughly the size of a small virus, even. So you have an atom that's just, a few Bohr radii, and then it becomes as huge as, micrometers. Now, it's also very clear that if you excite atoms, to these highly excited states, they also start to interact very strongly. And this is a resource of entanglement. And if you start to put in numbers and you come up with gates, these are papers that we wrote together with Misha Lukin now, you can see quite some time ago, but today these things are reality and also lead to very high fidelity gates. You can create interactions between these atoms and entangle them either as gates or by an interaction which is always on. And this is a way of engineering interactions between atoms, like, for example, the ones that we need for lattice gauge theory. Of course, at Harvard, this thing has been developed now. They're now really doing quantum computing with these things by having all of these arrays of atoms over here that can be moved around freely. And, we had these ideas of moving around a long time ago, but now to do it in an experiment, I mean, this is quite amazing. You can see all of these gate operations happening in parallel. This is now really quantum computation done in parallel on these qubits over here. And of course, a recent highlight from Harvard has been this error correction done in this way. And error correction at the end and doing fault-tolerant algorithms. Let me now go to the sort of a little bit more hardcore part, and then I will do this very quickly and just tell you what the basic ideas are. So we can create, using these tools, synthetic quantum matter. And they correspond to certain Hamiltonians, and they are really, really well controlled in the lab. That we have Rydberg interactions, we have a certain blockade radius, and by this we mean that we got atoms at a certain distance, and we would like to excite them. Only one can be excited, or the other can be excited. Exciting two of them would be too expensive, and we cannot actually do that. And this leads to a constraint, and it turns out that the Gauss law and lattice gauge theory can be sort of reformulated as a blockade constraint in this Rydberg tweezer arrays. And when we do now analog quantum simulation of what we call a quantum link model in this atom array, sort of the story goes like this, and I will be very brief here, that we have here 2D atom array, and there will be a certain blockade radius. So if one atom is over here, this is at the link of a honeycomb lattice, this is a Kagome lattice here, you can see other atoms like this one are out here, they cannot be excited. So this allows only certain configurations, and these configurations basically correspond to the Gauss law that we have to do in lattice gauge theories, and we can reformulate or reinterpret all of these different configurations of these atoms being on different lattice as charges and strings. And let me now try to explain this table over here, but show you what we expect from the theory by taking these Rydberg models and simulating that and translating the pictures into the language of lattice gauge theories. You can see over here that this would correspond to the case that we have a defect over here, defect over here. This is really punching holes in this synthetic quantum matter. And now this is theoretical calculation. The string develops, and over here you are in the regime by controlling your laser parameters where this string is broken. The potential for that is exactly what you expect. You can see the string tension and then the breaking of the string. This is reflected in this design of the model that we have over here. Then you go to Quera, to your friends, and there will be now different string configurations. You do theory, you get a certain phase diagram as a function of string tension and mass. There's a string, and there's a broken string over here. And then you can, go to the experiment. You indeed see that this blue regime goes roughly to that over here. This corresponds to this string. And then we have, of course, also here broken strings. The bottom line of the whole story, to sort of cut the whole story short, is this, that we see in the experiment as the ground state, the one, where we have here strings, or then we have broken strings. You can see here a broken string, only one configuration is over here, whereas over here you can see all of them somehow present. So this needs, of course, now more detailed discussion, but I think that the take-home message at this point is that, these quantum simulators that we have at the moment in the lab, they may be small, they may be toy models, but they already allow us right now to see phenomena that are highly non-trivial, and it will up to us in the coming years to develop all of these things. We can also do that for dynamics, what you can see over here. And if I want to conclude, I would simply say that, well, one of the big next steps will be, of course, that we really do fault-tolerant quantum computation. And, of course, at the same time, then you have to develop things like high-fidelity gates and finally reaching, of course, what our ultimate dream is, namely to go to the regime where for a useful or a relevant problem, we are able to do quantum computations that are, at the end, then, beyond what we can do classically. And of course, there have been examples in the past, but we really would like to push it at a point where we can compute something that hopefully will be a physical discovery. And I think we are maybe not too far away. With this, I would like to thank you for your attention.
Thank you very much, Zoller. We will have questions later. Let me introduce the next speaker, Professor Xiaogang Wen. Professor Wen is a renowned condensed matter theorist and Cecil and Ida Green Professor of Physics at the Massachusetts Institute of Technology. He graduated from the University of Science and Technology in China and then received his PhD from Princeton. Professor Wen's research has led to a fundamental shift in our understanding of strongly correlated condensed matter systems. He introduced the notion of topological order and symmetry-protected topological orders to describe a new class of quantum matters beyond Landau symmetry breaking theory. He discovered C2 spin liquid, the simplest example of topological order, as well as non-abelian statistics in a class of 2+1D topological ordered wave functions. He developed the string net theory of topological order, which led to the emergence of gauge boson and fermion. The string net theory provided a way to understand and unify gauge interaction and Fermi statistics, and led to a new type of unified theory using quantum information to unify all elementary particles. Professor Wen received the Oliver Buckley Condensed Matter Physics Prize and the Dirac Medal. His work continues to influence and inspire researchers in the field of quantum physics and condensed matter theory. The title of his lecture is The Origin of Light and Other Elementary Particles, Unification of Matter and Information. Professor Wen.
Yeah, it's really a great honor to speak here in the Future Science Prize week. And the Future Science Prize is really a celebration for the advance of science and its application. And today I'm going to talk about the origin of light and other elementary particle and the unification between information and the matter. So let's start from a bigger question. We know our world is very rich and very complex. And so there's a question is that where those rich and complex words come from and how to understand them. And the physics is a development of physics is via the cycle of discovery and and unification. So we have more and more powerful experiments, discover a lot more phenomena. When you have too many new phenomena, too many new discovery, we want to understand them better. Then we want to unify them under some simple unified framework. And so each unification, the big unification, actually represents a revolution in physics. So in this, through this revolution, we may each revolution may bring us into a new world where there's some fundamental concept. Some fundamental concept is changed, and the mathematical formulation also changed. So the whole worldview is changed. So let me just give some example. So the first revolution in physics, we can call it a mechanical revolution. What they unified? They unified this the falling apple on the Earth and the planet motion in the sky. So these two seemingly very different phenomena actually have the same reason. That is Newton's law of physics. So after this Newton's mechanical revolution, and our worldview is that everything is made of particles. And Newton's law governs the motion of a particle, and the collection particle explain everything we see. Okay. And there we have also, in this Newton's mechanical revolution, we also need a new mathematics. Because Newton's new phenomena they encounter is a curved motion. So we have to describe curved motion to write down his theory. Newton has to do that. But unfortunately, at that time, we don't have a mathematics to describe curved motion. So facing this new phenomena, Newton had to invent a new mathematics, which is called the calculus. Then after he invented calculus, then he can write down his theory. So actually, the introduction of new mathematics is a sign that the physicists encounter a really new world. We are facing a new revolution, and so we need a fundamental change our understanding. The next revolution is, I will call this electromagnetic revolution. And in this revolution, Maxwell find that find a new type of matter, I will say that way. Remember, in Newton's worldview, everything is made by particles. But Maxwell said that, oh, that's not quite true. There's another kind of matter, is light. Light is a kind of a wave-like matter, not the particle-like. And they satisfy a very different law, the Maxwell equation. And here, the new mathematics is a fiber bundle. What they unified is this phenomenon of electricity. Sorry. Yeah, electricity, the magnetism, and the light. Again, on the face value, they are so different. The magnetism, electricity, light is totally unrelated. But actually, they are the same thing. They're reflection of the same thing. They're all reflection of this wave-like matter. Then we have this relativity or revolution. So Einstein basically pointed out that in addition to light wave, there's another kind of wave-like matter, which actually is a deformation of a space. Even space itself can be deformed, can be dynamical, which gave rise to gravitational force. And here, the new mathematics for this space deformation, or for this second kind of wave-like matter, is a Riemann's geometry. The fourth revolution I would call the quantum revolution. In this revolution, we find that the spectrum of atoms and this diffraction of electron and the black body radiation, again, those are very, very different phenomena, are unified. They are really can be explained within the same framework. However, in this revolution, our worldview also changed. The Newton tells us everything is made by particles. The Maxwell and Einstein say, oh, there's another wave-like matter. But quantum theory tells us that actually particle-like matter and wave-like matter are the same thing. Those matter are particle, nor wave. And also, both particle and the wave. So it's all mixed up. It's very hard to swallow. What I mean by something is not particle, not wave, but also both particle, both wave. And this is really the magic of quantum superposition principle, which is shredding a cat, as Professor Zoller talked about. That's what makes it possible. So actually, the new worldview under quantum physics is that everything is made by the so-called wave particle-like matter, something mysterious. Okay. And however, if you really brainwashed by quantum theory, actually you will say that matter and information have very fundamental connection. Traditionally we think information is some kind of property carried by matter. Your information matter are very different thing. It cannot be mixed. But however, quantum theory tells us that the frequency is energy. It's just like how do I say that? It's just like the pound and the kilogram. Is a pound and kilogram actually the same thing describing weight? So quantum theory tells us that the frequency and energy are really two quantities actually describe the same thing. They are really the same. And it's really by this fundamental relation that the energy is given by the Planck constant times frequency. So this is a very fundamental connection between frequency and energy. Again, it's very, very mysterious. But however, if you think deeper, you realize that the frequency actually is a property of information. Something changed, anything changed is a frequency. But energy is a property for matter, especially according to relativity. The energy and the mass, they all unified. They really just is a property of matter. So quantum theory of Planck constant connect the fundamental property of information to the fundamental property of matter. Basically tell us information is matter, matter is information. And so this really come to this belief that there should be a unification of matter and information, or maybe matter coming from information. But how this is possible? Okay. And the traditional view of matter is this reductionist. We view the space as empty stage. The matter are actor on the stage, and this actor can be divided to smaller and smaller pieces. But however, in the modern time, this emergence of approach or this point of view became more popular. So in this approach, we view space itself is not an empty stage. Space itself is actor. Space is a dynamic medium. And this medium made by qubits. Qubits is the most fundamental, simplest building block in quantum mechanics. There's nothing simpler than qubits. So the space actually can be viewed as an ocean of qubits, like this picture. There can be 0 and 1s, and they interact. And this is very much like the philosophy. There's a 太极 and a 两仪. 太极 actually is a qubits. The 两仪 is a 2 value of qubits. And the 八卦 means 3 qubits. But actually our universe is, I don't know, I can see that have 10 to the 120 qubits. So there's much more than 八卦. But when you have so many qubits, some wonderful thing can happen. So actually, our universe is very, very complex and have a lot of many fundamental properties. And I list them as this 8 wonders of universe. And like this, like you have identical particle. There's a wave satisfy Maxwell equation. That's a Maxwell's contribution. And there's also a wave satisfy Yang-Mills equation describing the strong and the weak interaction. And then we have this mysterious particle called the electron quark, which have a Fermi statistics. Again, something very weird quantum effect. And they have a fractional angular momentum. And also, we certainly have a wave satisfy the Einstein equation. That's just another wave. So there's a bigger question. Can we use qubits to explain all those mysterious properties? You know, and the mainstream theory in physics tell us that no, those properties are so fundamental, and they are so fundamental, so mysterious, there's no explanation for them. So we should just accept them as something given to us, and then don't ask where they come from. But however, in the quantum information age, in particular, when we build these quantum simulators, maybe those kind of things can be simulated, can be understood via qubits. So that's this quantum simulator Professor Zoller talked about, may be able to simulate and explain those fundamental, even fundamental properties of a universe. And you know, after Maxwell wrote down his wave equation, and people have asked this kind of question. You know, if you think a light is a wave, then what is a wavy? You know, and then there's people search for such a media whose deformation, whose wave gave rise to the light wave, and failed. And actually, there's also standard theory. You know, this media was assumed to exist. It even have a name called ether. And people looking for this very special media, ether, whose deformation gave rise to a light wave. And people couldn't find it. And even have an experiment to show ether cannot exist. So therefore, the standard theory that ether do not exist, and there's no media which can produce a light wave, a light really fundamental, you know. And so indeed, in condensed matter physics, we really study many, many materials and study all kinds of waves in those materials, and none of them such a Maxwell equation. So it's a very frustrating experience. We just couldn't find anything which produced a Maxwell equation. But however, the recent progress is that we realize that the material we're looking for are actually more classical. They describe by symmetry breaking of a Landau. Actually, as a quantum material, there's a new kind of organization that the qubits may have a lot of entanglement, may be highly entangled. So those highly entangled organizations are called a topological order. So this kind of organization is not studied before. So maybe we have a new hope. Maybe with this new kind of organization, this kind of material may be able to produce a light wave. So, so one of this highly entangled material can be made by this string. You know, we can imagine we have this media where the qubits with the empty dot is 0 and the black dot is 1. And this 1 may form a string. And the string may just dance around and form a string liquid. But that certainly is a simple way to say dancing around form a string liquid. A more precise way to say that, according to Peter Zoller's talk, is that there are superposition of all different string configuration. And that's gives rise to the quantum liquid. And this kind of superposition of the dancing pattern of a string configuration is actually have a long-range entanglement. It's representing a topological ordered material. And this kind of material probably can give rise to light, give rise to Maxwell equation. And that's indeed the case. So let's consider a string liquid. So this animation just representing a string liquid. It's kind of superposition of all kind of string configuration. So when you have this string liquid, remember strings are formed by qubits. So those are really entangled pattern of qubits. Then you may ask, what is the deformation? What is the wave inside this string liquid? It's very simple, a density wave of a string. Some region, you may have a more string, other region have a less string, okay? And then because it's a string, so string have a direction. So therefore, to describe string density, we need a so-called a vector field. So here you have more string in this direction, there you have a more string, but in that direction. So there's a vector field to describe string density. And this vector field is also very special because the string density can only change in the direction perpendicular to the string. Along the string density cannot change because in order for string density to change along the string have to end, have to break. If string do not break, always form loops, then along the direction string, the density cannot change. But in the direction perpendicular to the string density can change, which is really this picture. You can, in the direction perpendicular to the string, density can change. Mathematically, it's really say that this vector field is divergenceless. Actually, that's one of Maxwell's equation. The electric field are divergenceless. So actually, electric field in Maxwell equation actually is a string density. And so this kind of density wave naturally satisfies the Maxwell equation. Okay. So therefore, this long-range entangled string liquid naturally explain the origin of Maxwell equation. We don't need to view light as a fundamental. It's just a property of entangled qubits. If a qubit is entangled in a certain way, like in this string liquid way, then we will have a Maxwell equation. Okay. So that suggests that maybe our vacuum is indeed a qubit ocean which entangled as a string liquid, and that's why we see the Maxwell equation. That's why we have a light. The light coming from entangled qubits in our vacuum. Okay. Then we can actually make the story even richer. The light is just electromagnetic interaction. We also have a weak and a strong interaction. They are described by different equation called the Yang-Mills equation. And actually, we can also produce this kind of wave, Yang-Mills wave, which we just allow the string to connect, to branch, and form. This is called string net liquid. And the how string connect encode the information so-called the gauge group and etc. And actually, string net liquid can go beyond even Yang-Mills equation. It's the most general string net configuration actually are described by so-called the fusion category, a very abstract mathematics, which seems start to enter physics. This category theory start to enter physics to describe this entanglement. Okay, so therefore, this string net liquid can be used to produce the weak and strong interaction. Okay. Then you may say, should I really believe this? Or maybe it's just a story. Maybe our vacuum is really not a string liquid. Maybe not string net liquid. Well, if you believe this our vacuum is string net liquid, we can even explain the origin of electron and quarks. And so we don't need to introduce any new concept. Just a string net liquid which produce light and weak interaction, strong interaction, also automatically produce electron and quarks. They are end of a string. You may say string is something extended. The end string are extended. And the electron quark are point particles. So they are not like end of string. You can see the string. But actually, when you have an open string embedded in the background of a closed string liquid, we don't see the middle part of open string. They are kind of blend in with the background of string liquid. Only the end string shows up. So therefore, when you have open string in the background of closed string liquid, it's just like a two particle given by the end of a string. And this kind of particle interact with a string density wave, just like a charge interact with an electric field. And also, this kind of end string can even carry a very mysterious property called Fermi statistics. So I won't explain what is Fermi statistics, but just as it's an extremely mysterious property in quantum theory, but actually it can be explained very naturally using end of string. Okay. So therefore, if you're using this kind of a qubits ocean point of view, actually we can explain the 7 out of 8 wonder. All the 7 out of 8 wonder can be viewed as a property of a highly entangled qubits. And however, at the moment, we don't know how to get the Einstein equation. We couldn't find the entanglement pattern whose deformation gave rise to Einstein equation. So we tried, but so far without success. Maybe they exist. Maybe we need something more fundamental change. So that's an open question. So according to this quantum information unification of a matter, or this new point of view, I call this new point of view like a second quantum revolution. So in this, the world view will be the space is like an ocean with qubits, and the qubits may be highly entangled in the way of a string net entanglement, and this fluctuation for a string net can give rise to photon, gluon. There's an electromagnetic interaction, and there's a strong weak interaction. And the end of string is electron or quark. So this represents unification. Remember, the grand unification unify all 3 fundamental interactions. Weak, strong, and electromagnetic interaction are unified. And this theory is called the grand unified theory. And however, this qubit ocean theory is even unified more. They not only unify all the 3 interactions, it's also unify the interaction with matter. Electron and quark are unified with the interaction. Okay, so it's a grand square unification. So it's just so almost everything is unified, but except gravity. Yeah, we do have trouble with gravity at the moment. So therefore, this so-called second revolution unify many different things. It also have a new mathematics. That is here similar to Newton's time. Newton are facing curved motion. That's a natural phenomena. He had to invent calculus to describe curved motion. Here, what we are facing is a many-body entanglement. We have many degree freedom. They have lots of entanglement. They are really entangled. So then we are facing the issue of how to use a mathematical language or mathematical theory, or which mathematical theory describing many-body entanglement. That is the challenge we are facing. And in the sorry. So there's unentangled states. So we have many body states, like many qubits. There's a particular organization, very simple, called unentangled organization. Like a spin all pointing up, or maybe spin is up and down, up and down. So those are unentangled organization. And this kind of like a classical organization. This kind of classical organization is described by the symmetry and the group. So we're gonna introducing the group to physics with a lot of resistance. Physicists say we don't need a group theory. Only mathematicians need a group theory. And but now physicists embrace group theory. And however, when you're facing the long-range entangled states, the symmetry and the group no longer enough. We need something new, something different. And this different thing has to be the braid fusion higher category, some kind of category theory describing this many-body entanglement. So usually we talk about the 4 revolutions. Usually mathematicians are ahead of physicists. When physicists discover a new phenomenon, the mathematics describing that phenomenon usually have been invented like 100 years ago. Except Newton's time, where the mathematician is not ahead of physics. And this time, it's about the same. The higher category theory is still developing. So therefore, at the moment, this physics and mathematics can develop together to try to understand the phenomena of many-body entanglement. And there's another, so in addition to unentangled organization and highly entangled organization, there's so-called short-range entangled organization. And in this kind of short-range entangled organization of quantum information are really described by, again, some modern mathematics called the group cohomology theory. So really, the quantum entanglement is really a new phenomenon. And a lot of very abstract modern mathematics enter physics to describe this new phenomena. Yeah, here I'd like to point out that actually the three of the pioneers developing those theories are really in this room. And Kong Liang is developed the hierarchical theory for the many-body entanglement. And Zhengchen Gu and Xie Chen really developed a theory about this long-range entanglement, and also developed a theory for this group homology theory. Kong Liang is kind of local; he's from Shenzhen, and Zhengchen Gu is even more local. He's from this Chinese University of Hong Kong. Yeah. So to summarize, that the matter and the space is coming from quantum information. It's almost like the movie Matrix. In the movie, they describe this the virtual world can be as real as a real world. But actually, this matrix is not quite right. What happens is this information world is a real world. Our material world is a virtual world. So matrix get it flipped. And if you're using this picture, all these interaction Fermi statistics, and they all really reflection of a many-body entanglement. So that's how powerful many-body entanglement can be. And that's how powerful quantum simulator can be. Actually, quantum simulator can simulate everything, maybe even gravity. So we don't know. Yeah. Thank you.
Thank you. Next, I would like to introduce Professor Robert Huang Xinyuan. And he's a bright young star in the quantum information, and he contributes his groundbreaking work in the field of quantum mechanics, in the quantum machine machine learning, has earned him international recognition. He's currently a senior research scientist at Google Quantum AI and a visiting scientist at MIT. He will soon join the faculty at Caltech. Professor Huang's work is characterized by a rigorous theoretical approach combined with experimental feasibility, where he investigates how scientists, machine, and future quantum computers could learn models of our quantum universe. He leveraged quantum information theory, quantum many-body physics, learning theory, and complex theory to address the following question. When can quantum machines learn and predict better than classical machines? How to accelerate and automate the development of quantum and physical science? What physical phenomena can classical versus quantum machines learn and discover? Professor Huang's research has the potential to revolutionize our understanding of quantum systems and their interaction with classical counterparts. offering insights that could lead to significant advancements in quantum computing and information science. His ultimate goal is to build quantum machine capable to discovering new facets of our universe beyond the capability of humans and classical machines. The title of his lecture is Learning in the Quantum Universe. Professor Huang.
Yeah, thank you so much for the introduction and also the invitation to attend this Future Science Prize Week. I'm黄信元, and today I'll be talking about learning in the quantum universe, an emerging field within quantum information science. So as scientists, we all know that a central goal of science is to learn how our universe operates. And so as we have seen, our universe is inherently quantum mechanical, and hence the ability to efficiently learn in the quantum world could lead to many scientific and technological advances. For example, if we can efficiently predict how a collection of molecules will interact with one another, then it can help us design better catalysts and pharmaceutics. If we can efficiently learn the topological properties of quantum many-body systems, it can also help us gain new insights into exotic quantum matter. And finally, if we can efficiently learn the inner workings on how to control quantum devices, it can help us accelerate the development of quantum technology that will advance sensing, communication, as well as computation. And hence, to accelerate and to automate the development of quantum science, it is very critical to understand how we can design better algorithms to learn in the quantum universe, which is the main topic of my talk. Because learning is going to play a big role in my talk, I would like to first start out by defining what learning is. So learning is a combination of the following information processing capability. First, there's going to be an unknown aspect of our universe that we would like to learn about. It could be the state of the quantum system that we're creating in the lab. It could also be an unknown dynamics happening in nature. It can also be the phase diagram of a material, etc. We receive information about this unknown by doing measurements and experiments. We then process these information to form predictive models, which can be a theory, like electromagnetic theory. It could also be a complicated model, such as a neural network. We store these models such that subsequently we utilize these models to make accurate prediction about the unknown in new scenarios that we are interested in. The overarching question of this field is the following. How can we efficiently learn in the quantum universe? And in recent years, the development can be broadly categorized into two directions. One is learning with classical machines, where we try to understand how we can utilize current technology, classical computers, etc., in order to learn in the quantum world. And then the second direction, we try to envision having advanced quantum technology and understand how using quantum machines can help us better learn in the quantum world. So let me begin with learning using classical machines. Here, some of the central questions include, what can classical machines learn? And also, if we have a classical machine that can learn, can they outperform classical machines that cannot learn? So while it's a priori not clear how to answer this, I would like to first start out by asking an even more foundational question. How can classical machines see quantum many-body systems? So from the talks by Xiaogang Wen and also Peter Zoller, we can see that quantum many-body system can, in this crazy superposition over exponentially different classical states. And when a classical machine tries to see the quantum many-body system, it will cause collapse. And it would just collapse into one of the classical state. And hence, a priori, a classical machine is unable to see these enormous superposition and entanglement inside quantum systems. However, there's still hope that perhaps using a more clever learning strategy, a classical machines will be able to see all of that. But to be more precise, what do we mean by seeing? One operational definition of seeing is the following. we try to convert the quantum system into some classical representation such that that representation accurately captures many properties of the quantum system. And hence, the classical machines, even though it cannot see the quantum system in its original form, it can just look at this classical representation in order to understand, reason, and manipulate the quantum system. The standard approach for learning or seeing quantum system is known as quantum state tomography. The idea is to learn the standard canonical representation of a many-qubit state. And for those of you who have taken quantum mechanics or know a little bit about it, this canonical representation is known as the density matrix, and it's an exponentially large matrix. It's of size 2 to the n by 2 to the n with certain constraint. And because we're inherently trying to learn and to see this exponentially large matrix, even the optimal protocol will require a resource that scales exponentially in system size for all of its different aspects. For example, sample complexity, also known as how many measurements do we need in order to learn the state, grows as 2 to the 2n. And the memory storage, the classical post-processing time, all of that grows exponential in system size. So while quantum state tomography, which has been around for many decades, have been very useful for the early stage of quantum technology, because at that stage, people are just trying to build and control a few qubit system. In the current era, the experimentalists have been able to create a few hundreds or even a few thousand qubit. And in those cases, if one plug in the number, if n equal to 1,000, then 2 to the 2,000 is already way beyond what we can capable of doing. And hence, we want to have something that's much better than quantum state tomography in learning and seeing quantum systems. So ideally, what we want is the following. We want to find a provably efficient procedure that allows us to do the following two steps. First, it will learn a classical representation of this state by performing a small number of measurements that do not scale exponentially in system size. And then our hope is that this classical representation accurately captures a huge number of properties of the original quantum state, and hence by looking at that representation, we can know and understand anything about the system. However, note that, as we have seen, if the goal is to learn the canonical representation or density metrics or wave function, one requires an exponential number of experiments. And hence, to achieve this, we have to move away from the standard description that we learned from quantum mechanics. We have to find a more succinct and more efficient classical representation that allows us to describe quantum system. A priori, it's not entirely clear how we will be able to do so. However, luckily, 4 years ago, together with Richard Kuhn and John Preskill, we stumbled across this surprisingly simple yet powerful formalism called the classical shadow formalism that allows us to achieve what we want. Particularly in this work, we proved that for any quantum system, a classical machine can learn a very efficient and succinct classical representation of the quantum state by performing only a few number of measurements. And furthermore, this classical representation accurately captures a wide range of properties of the quantum state. For example, if one plug in a number, we set m to be, say, an exponentially large number, and we can see that the number of measurements is still only linear instead of exponential. And hence, this classical shadow formalism allows classical machines to see and understand quantum systems. And furthermore, this is not just a theoretical concept, even though originally we proposed it to be, but can actually be done easily on a lot of experimental platforms, and there have been a lot of demonstration utilizing this new framework to describe quantum systems. And one of the reasons is because the procedure is actually very simple. All we have to do is the following steps. In each measurement, we sample a random quantum evolution, also known as unitary, that scrambles the quantum system. Now, after that, what we would do is we would measure the system, causing it to collapse into a classical state. So after scrambling, the quantum system will be in a superposition over exponentially many different things. Now, when we measure, we will just see one of the classical state. And then what we do is we store this classical shadow, which is given by applying the inverse of the quantum evolution to the classical state that we got. So for those of you who are kind of careful, this classical shadow is still a quantum state. However, we are going to restrict ourselves to quantum evolution that is easy to simulate on classical computer, and hence this representation Si can be stored efficiently on classical computer. Broadly speaking, one can understood this measurement procedure using the illustration shown to the right. We can think of the quantum system as this very high-dimensional object. It's an exponentially high-dimensional object from a classical perspective. Here, it's just shown as a three-dimensional object. Every time when we do a measurement, what we're doing is we're essentially looking at this quantum object from a random angle determined by this random quantum evolution, random unitary U. And we are going to project it into the classical space, casting a shadow in the classical space. So if we do it for once, it's not going to be very helpful. However, if we do it for a few times, then suddenly we can start getting a good sense of what this exponentially high-dimensional quantum system actually is. And by looking at these classical shadows, one will be able to see and understand quantum systems. And then, utilizing this intuition, one can combine it with theory of machine learning, as well as high-dimensional probability and quantum information theory to establish this theorem shown here. And over the past 4 years, our community has really found a lot of very exciting and creative application of this new classical representation for describing quantum systems. One of the more direct application is in benchmarking quantum systems. So note that quantum systems are extremely fragile. Even just a tiny bit of heating up or some photons coming in can just completely destroy the quantum system. And hence, in practice, in developing quantum technology, it is very important to be able to efficiently check how good our quantum system is. And that's known as benchmarking. So for example, on this plot shown to the right, the x-axis corresponds to the probability of error that is happening to our quantum system. And the y-axis is the fidelity. So fidelity of 1 is the best, while a 0 is the lowest fidelity. And as we can see, as the probability of error increases, the fidelity would go down as estimated. So the correct behavior is given by this dotted line. And as we can see, using this classical shadow framework, one can accurately predict this property due to the rigorous guarantee. Here we also compare it with a very powerful heuristic known as neural network quantum state tomography, where one tried to utilize deep learning models to learn quantum systems. While this method works in many cases, in some cases, it can fail very miserably due to the neural network hallucinating, as one might have already seen a lot of times when playing with LLMs. But here, for example, we can see that the fidelity that the neural network reporting is much higher than the true one. And hence, it could give a false confidence to the experimentalists, causing them potentially to make incorrect scientific claims. However, by utilizing a rigorous protocol, one is able to avoid that. The community has also been using classical shadows for doing quantum simulation, such as the simulation of complex molecules. In a paper published by Google Quantum AI in Nature in 2022, Huggins et al. Were able to simulate some complicated molecules using an advanced hybrid quantum classical algorithm. And in their protocol, they require extracting a huge amount of properties from their quantum system in order to guide a classical algorithm running on the side. However, if one just do it naively, then it would take an extraordinarily long time. They were able to utilize this classical shadow formalism to first construct this classical representation and then predict all of its properties from that classical representation. More broadly speaking, classical shadow can be thought of as a new way of converting quantum information to classical information. So if there is some quantum system we would like to understand, we can apply this tool, do these randomized measurements, create these classical representation, and now we can apply our favorite classical computational techniques in order to address the quantum problem. For example, by combining classical ML and classical shadow, we were able to provide a provably efficient algorithm for classifying quantum phases of matter, as well as predicting ground states of quantum many-body systems, as I will briefly talk about soon. So now, after answering this question, showcasing how classical machines can actually see into quantum system by casting these classical shadows and by analyzing these classical shadows, we can now move on to a more ambitious question. Can classical machines utilize its ability to see quantum system to learn from quantum experiments in order to solve some very challenging problems arising in quantum physics, and hopefully yield better solutions than any non-machine learning algorithm, establishing an advantage of ML versus non-ML algorithms in a physically relevant setting. So that's what we essentially looked at in this paper published in Science 2022, where we considered the problem of predicting ground state, which is one of the most ubiquitous problems in quantum physics, dating back to 100 years ago, when quantum mechanics was just emerging. So in this task, we're given some parameters that describe a physical system, and note that every physical system is a quantum many-body system. So a parameter describes a quantum many-body system, and our goal is to predict the ground state of that physical system, the lowest energy state, the most stable state. And this problem has been well studied for a very long time, and there are a lot of evidence showing and proofs showing that this problem is very hard for classical algorithms. And one of the reasons is because classical algorithms cannot really simulate and process quantum systems very well. However, one can still ask, is it possible that even though classical algorithm fails, classical ML algorithm can still do something useful for this task? In order to train classical ML algorithm, we have to feed it with some training data. One natural choice is the following. We just give him a bunch of existing physical system and the corresponding ground state. But then one could immediately ask, the ground states of a quantum many-body system is a quantum state. So how do we give a classical machine a quantum state? It cannot process that. And here's classical shadow can just be directly applied. In order to feed it into classical machine, we just first turn the quantum system into its classical shadow representation, and then the classical machine will be able to process that and learn from it. And the hope is that after learning from these training data, the classical machine learning algorithm would be able to predict the ground state for a new physical system that it have never seen, we have never created in the lab, and in a very accurate manner. So now let's go back to a more rigorous statement for classical algorithm. Using standard complexity theoretic techniques, one can prove that no randomized classical algorithm can achieve a good prediction error, a prediction error less than or equal to 1/4 within polynomial time. Meaning that if one has write down a classical algorithm that runs in polynomial time, which is efficient, then the prediction error must be greater than 1/4, which is pretty large. And this is true even when one restricts the classical algorithm to only apply to, say, 2D material or 3D material, etc., under various restrictions. However, what we found was a seemingly contradictory theorem, which states that even though classical algorithm cannot solve this problem, we can write down a classical ML algorithm trained with data that can achieve a prediction error that's much lower than 1/4, using just a small amount of training data and an almost linear computational time. And this classical ML algorithm works in any constant dimension, meaning that it can work in 2D material, 3D material, and work in regimes that's much broader than the classical algorithm fell on. And hence, together, the proposition of the theorem showcases this strange conclusion, where one can rigorously prove that a classical machine learning algorithm can predict ground states of new physical systems much better than any classical algorithm. So one might ask, how is that possible? How could this be? Aren't classical ML algorithms just a type of classical algorithm? How can they be more useful than these broader family of algorithms? And if one look closely at the inner working of classical ML algorithm, one will see the answer. The answer is that a classical ML algorithm can learn from data, and all it has to do to solve problem is to generalize from data, which can be much easier than computing everything from scratch. And in one of our previous paper, Power of Data in Quantum Machine Learning, we proved that data contains computational power. For example, nature is operating quantum mechanically, and hence if we learn from experiments, we will gather some quantum computational power from nature. And hence, it can improve the computational power of those that learn from it, yielding a complexity theoretic diagram that looks like this. So here, each circle corresponds to the set of problems that can be solved by either classical algorithm or quantum algorithm, and classical ML algorithm trained with data. And essentially, if classical ML algorithm is able to obtain data that is not efficiently generatable on quantum computers, then it will be able to solve problems that's beyond both classical algorithm and quantum algorithms. Together, these results show that classical ML algorithm can indeed perform much better than any non-machine learning algorithm, and classical machines are actually quite powerful in seeing and learning in the quantum universe. Now we would like to move on to the next part, which is, what about learning using quantum machines? If in the future we have a very powerful quantum computer that can learn, can these quantum machines learn faster and or predict more accurately than classical machines? To answer this question, we have to first define what we mean by a classical and quantum learning machine. And that can be kind of abstractly captured by this notion called classical learning agent or classical agent and quantum agent. So the classical agent can learn about our world by receiving classical information through measurements, processing these information using classical computers, and storing the information after processing in classical memory, and utilize these capabilities to learn and make prediction about our universe. In the future, as quantum technologies start to mature, we can imagine giving rise to these powerful quantum learning agents, or one can intuitively think of them as a powerful quantum AI model, that can receive quantum information from our world using quantum sensors, process them using quantum computation, and storing them in quantum memory. And given this dichotomy, one can now ask the following question. Can quantum learning agents, or quantum machine, yield an exponential quantum advantage in learning about our world over classical agents? While this is a very important question for this field at the intersection of quantum physics and learning, I would also say this question is of much broader interest, because this question is equivalent to asking if in the future, whether quantum technology can fundamentally alter our ability to learn about our physical universe. Apparently, it's not clear that this should be the case, since we have seen that classical machines are even very powerful in learning to solve quantum many-body problems. However, throughout several recent works that combines ideas from theoretical physics, theoretical computer science, and random metric theory, etc., we were able to develop a new mathematical framework that allows us to establish and prove exponential quantum advantage in many learning problems, including predicting observables, uncovering hidden symmetry in the real world, learning approximate models of dynamics, etc. The one thing to note is that in quantum technology, a lot of times quantum advantage will die when there's noise in the quantum technology, in the quantum computer, for example. However, what we found was that these new quantum advantages actually can survive even in noisy quantum computers, supported by rigorous mathematical analysis in a work with Steve Lamia and John Preskill, as well as demonstrated experimentally in collaboration with Google Quantum AI. So here I wanted to showcase some of the experimental demonstration on Google's Sycamore quantum computer, demonstrating the advantage in learning about states. So here on the plot shown to the right, the x-axis is the system size, how many constituents is in the physical system we would like to learn about. The y-axis is the number of experiments to achieve a good prediction accuracy. The gray crosses corresponds to the performance of the best known classical learning agent for learning physical systems. And as you can see, as system size grows, the number of experiments grows exponentially. The dashed line corresponds to a rigorous lower bound that can be proven utilizing this new mathematical framework that I described. That applies to any classical agents, meaning that even in the future, if we found some clever ways to learn physical system using classical learning agent, it will still be above this dashed line. On the other hand, the quantum learning agent that we implemented on Google's quantum computer provides a performance that looks like this, which at the largest system size that we looked at surpasses the rigorous lower bound by orders of magnitude, showcasing that quantum agents can learn much, much more efficiently than classical agents. Here's another demonstration on Sycamore quantum computer for the advantage in learning about dynamics. The goal here is to try to see if this learning agent is able to discover something on its own. And here the goal for the agents is to uncover some hidden symmetry in the physical dynamics. To both classical and quantum agents, they will be given access to a set of distinct unknown many-body dynamics. half of the dynamics satisfy time reversal symmetry, also known as T-symmetry, while the other half are just some general random dynamics that's happening. And the hope and the goal is that the learning agents can just do experiments on its own, try to play with these dynamics, and at the end, in an unsupervised fashion, try to figure out and discover the hidden symmetry for these collection of dynamics. And as we can see from the plot to the right, the quantum learning agents is able to efficiently figure out in a purely unsupervised fashion that the collection of dynamics, half of which are time reversal symmetric, while the other half are just general dynamics. On the other hand, the classical learning agent fails to do so. And this is also supported by our mathematical theorems. And one can see that the classical learning agent is unable to uncover this hidden symmetry, and everything is just a big blob. So this provides a proof of principle experiment showcasing that quantum agent or quantum machine is able to discover things that are invisible to classical machines. And together, all of these results answer this question in the affirmative, showcasing and demonstrating that quantum machines can learn exponentially faster and predicting much more accurately than classical machines in learning about our universe. So together, all of these results paints the following picture. It shows that, first, utilizing clever techniques, classical machines can be surprisingly powerful at learning and making prediction in the quantum universe. Even though there are still problems that classical machines cannot solve, it can see a lot of things in quantum systems and solve some very hard problems after learning from experiments. However, we also see that quantum machines can be provably and exponentially more powerful in learning about our world. And finally, I would like to conclude my talk with the broad long-term ambitions that might not be achievable within 50 years. Maybe we need 100 years to do so. And these long-term ambitions are the following. First, we would like to build on what we have so far about learning, to continue developing our understanding of learning to accelerate and automate scientific discovery. And perhaps one day, we will be able to give rise to an algorithmic theory of science, meaning that we can write down a rigorous algorithm such that by running that algorithm, one will be able to discover everything that's left to be discovered in the scientific world. And if we can make some progress towards the first point, and then quantum technology continue to develop, in the future, maybe one day we will be able to build a quantum machine that is capable of learning and discovering new facets of our universe beyond what can be visible used by humans and classical machines combined. That's it for my talk. Thank you so much for listening.
Thank you. Now we are going to move on to classical world. Professor Li柯伽is a prominent professor of astrophysics in Peking University, who made significant contributions in pulsar research and gravitational wave detection. Professor Li completed his bachelor and PhD degree at the Peking University, and subsequently he was a postdoctoral research scientist at the Max Planck Institute for Radio Astronomy in Germany. As one of the founders of the Chinese Pulsar Timing Array, CPTA, Professor Li has played a critical role in advancing the field of pulsar timing and gravitational wave detection. His research focused on the detection of fundamental physical processes through pulsar timing, radiation mechanism, and relativistic plasma physics. Notably, his team published groundbreaking finding regarding the origin of repeated fast radio bursts, making several significant firsts in the field. Professor Li's dedication to understanding the universe through pulsar observations has positioned him as a leading figure in the quest to detect nanohertz gravitational waves, a challenging endeavor that has recently seen promising results. Professor Li received the 2022 Science Exploration Award, and the topic of Professor Li's lecture is Progress of the Chinese Pulsar Timing Array, which he will share his insight into the latest development in pulsar timing and their implication for gravitational wave astronomy. Thank you.
So hello, everyone. My name is KJ Li, and I'm now working at Peking University and Chinese Academy of Science National Astronomical Observatory. And although I'm the speaker today, actually behind me there is a big team working on pulsar timing array, Chinese pulsar timing array. So I will basically cover four major things today. First, why we want to detect nanohertz gravitational waves. For most of the time, gravity does not play any role, particular gravitational waves doesn't play any role in our normal life, right? Except that we fell off on the ground and break out the bones that relates to gravity. Besides that, we do not need the relativistic description of gravity or gravitational wave. But why we spend so much efforts to detect nanohertz gravitational wave? And the second thing is how we detect gravitational waves. It's a very long wavelength, low-frequency gravitational wave, how we make the instruments stabilize over a couple of years or probably 10 or 20 years. And the third, how is Chinese pulsar timing array is doing nowadays, and what will happen in the near future. Well, let's go from the first problem, why we want to detect nanohertz gravitational waves. If you look at the sky, in a dark place, you will see many, many stars over the sky in the night shining on the black patch of the sky. And people draw the picture about it, like this one. And all those stars you see in the nighttime are actually all close-by stars, mostly. They are actually in our own Milky Way. Most of the stars, about 2,000 you can see in the night, if you have very good eyesight. That's all nearly in our own Milky Way. So that's the size of our universe? Probably not. Well, how large is our universe? Let me give you an example. You can hold a piece of paper, punch a small, tiny hole with your pencil with a diameter of 0.5 millimeter and pull the paper away from you for 1 meter away, and you look through that hole, what you will see? If you have very, very, very good eyesight. Well, what I expect, nothing is black, right? But actually, people do the experiment back 2012 with Hubble telescope. This is what you will expect to see. All those bright little dots and fuzzy objects there are one galaxy, like our own Milky Way. So that's the size of the universe. If you continue to ask, beyond those things shining lights in the universe, where there are something else, the answer is yes. So suppose that this is our universe, the square box. Well, I do not know if the universe is a square box, but let's say that's our universe. And those material emitting lights or electric magnetic waves are actually occupy that small tiny portion of the whole universe. About 0.few% of the whole universe is those luminous materials. We know what they are and we see them. There are a couple of percent of the material. We know the material. We know those are the material of daily life, like from the baryons, and those material is called the baryon contents of the universe. It occupies a couple of percent of the whole universe. And the next portion occupy about 30% of the whole universe, and we don't know what they are. We know it's probably material, and people doing experiment in the cave down in the earth to shed away the other particles, try to search for this particular kind of particles. People do astronomical experiment to verify the property of this particular type of material, and people call this dark matters. There are a couple of candidates people proposed to understand what they are, and so far we have no detection for the real particle of dark matter. But we know they must exist because the universe is what we see now, and if you want to get what you see now, you need to put this in your big model. How about the rest 70%? Huge amount of the universe. Well, we don't know what they are. It's probably just a parameter in the equation, or it could be something we call dark energy. We know the general equation of state for this material, but what they are, whether they are a field or constant or some type of particular particle, we don't know. So that's our understanding of the universe. Something we see, something we know, something we probably know, and something we're not sure if it's really something material or not. The key question is how those material or matters come from, and where they come from. How the universe forms the current structures. If you look at the universe, it forms some very linked network-like structures. How the universe forms this structure. How we can directly trace those material not emitting lights. Does our universe contain defects? Or it's just a smooth, continuous, four-dimensional something? Is our law of physics apply to the very early universe? At the time when the universe is very tiny and the temperature is very high, where the physics law we know today still apply there? That's a key question. And we try to answer those questions from observational side of views. Here is a general idea about how a universe are formed. At the beginning, you have a big bang, and after a very tiny period called inflation, it starts to cool down and the universe expands. On the way universe starts to expand, the particle appears and a material appears, and due to the gravity, material being attracted to each other to form structures, and stars and the galaxies are then formed. That's a general picture of our current universe. To explore the interesting physics, answering those questions I proposed one page before, you really need to look into the universe when it's at a very early stage. How can you do that? Well, for that particular area, you won't be able to see it because it's hide behind the dark age, we call. And how we can know the physics happens on that stage. There's one technique called gravitational waves. Gravitational waves are kind of a wave generated by the acceleration of mass or acceleration of energy. So there are many ways to detect gravitational wave, from high frequency to very low frequency. At high frequency, on the ground, you can build laser interferometer, like ground-based interferometer called LIGO or Virgo, to detect the collision of stellar mass black holes. That generates a gravitational wave at a frequency about 100 Hertz. At lower frequency, when the period of the gravitational wave approach hours time scale, you cannot detect those gravitational waves on ground anymore. You have to go to space to have a much more stable environment. And in the space, if you have laser interferometry, you can detect gravitational wave down to a couple of hours. That time you will see the orbiting of the big black holes, and you can see a tail of cosmic string. What is cosmic string? I will explain later. At even lower frequency, the frequency of gravitational wave achieve a couple of years. The only known way to detect those gravitational waves is to utilize a celestial object called pulsars and use pulsar as a detector to search for gravitational waves. At this band, what you will see is you will see gravitational wave first astrophysically from those galaxies. And when the galaxy merge, there will be two big black holes in the center of the two galaxies. When they start to merge, you will see the orbiting and collision of the two black holes that will emit gravitational waves. And those gravitational waves happens in the frequency band of post-timing array. You can also see something called cosmic string. It's a universe defect. Basically, when the universe is cooled down, you sometimes have the edges on the phase transition. You can either have dot-like structure, line-like structure, or a surface-like structure. For the line-like structure, we call cosmic string. And for post-timing array, it's right on the peak of the cosmic string spectrum. So we are able to see if they do exist, we were able to see the gravitational waves from the cosmic string. And if we are lucky, we will be able to see the residual gravitational wave from the quantum fluctuation at the very beginning of the universe. So as a short summary, nanohertz gravitational wave can directly probing the universe structure formation. It can provide a bridge to look into the early universe, and it's sensitive to the universe defects. And also, it actually can do gravity theory test in the new parameter space to understand if our gravity theory works in different set of parameter space. Let me try to explain how we do that. So pulsars are discovered pretty new, actually. It was discovered in 1967 by Anthony Hewish and Jocelyn Bell. It's a star. We know it's a very small, we know the radius of the star is very small, it's about 10 kilometers, and the mass of the star is about 1 solar mass. It rotates, and it has magnetic field, so the radiation of the star is more like a lighthouse. So when the lighthouse sweep across your line of sight, you will see a bright pulse. That's exactly how the radio pulses are generated. And once on the Earth you have some telescope, you can measure the pulse and you can see those pulsars. Turns out that the pulsar rotation is very, very stable. Here I show you an example. Let's neglect the green and blue lines here, just focus on the yellow and the red line here. The red line here is actually the stability of current international atomic clock standard. So the higher the value is, the more unstable the system is. So at a very long time scale, the stability of the clock ensemble gets worse. For pulsars, we can compare to the International Atomic Clock Standard and also figure out how stable those pulsar systems are. That follows the yellow lines. On short time scale, the yellow curve lies above the red curve, so you know that the pulsar is not stable compared to the clock. But on long term, it's very stable. It can go down like 10 to minus 15-ish compared to the 1 or 2 order of magnitude improve compared to the current atomic standard. Once you have so many pulsars spreading across the whole Milky Way, nearly all the pulsars we observe in this talk are all in the Milky Ways. And on Earth, you have some telescope to observe those pulsars. You equivalently have many, many very accurate clock on the sky. And you can measure those clocks. And by correlating the signal together, you will be able to differentiate the contribution of various of signal. Let me give you an example. Suppose you have 2 pulsars very nearby on the sky. You see them, and gravitational waves come by and perturb the space-time background. Then the 2 signals pass through nearly the same path. So the contribution would be similar. If you correlate the pulse signal you see for these two pulsars, right, you will expect to see the positive correlation here. Because of the symmetry of gravitational wave, it tends to squeeze the x direction at the same time stretch the y direction, and compress the y direction and stretch the x direction. Then at 180 degree, the two pulsars will do similar things, right? So if you correlate the signal from two pulsars 180 degree apart from each other, the correlation coefficient would be still positive. But for two pulsars 90 degree apart from each other, you compress the y direction, you stretch the x direction, and you compress the x direction, and you stretch the y direction. So the 90 degree correlation would be negative. So this very specific curve, like this shape, is called Helling-Sand-Dance curve. If you find this correlation, you know that there is a gravitational wave like quadrupole correlation in your data sets, and you can use that technique to detect gravitational waves. Similarly, if your clock is not stable enough, you will see all the pulsar signals start to become late or earlier, and the correlation is angularly independent and be of positive values. If your Earth position or telescope position is incorrect, then you have this blue curve. It's called dipole correlation. You have positive correlation at 0 degree and negative correlation 180 degree. So you can separate different systematics. And because of using the same argument, we get the Helling-Sand-Dance curve from the symmetry of how gravitational wave perturbs the space-time. By extend the possible polarization or the way gravitational wave perturbs the space-time, you can actually have up to 6 different types of polarizations. And that's not in the general relativity. That's in the gravity theory besides general relativity. For those polarizations, you can have extra 3 types of correlation. By looking at those correlations, you can immediately test the gravity theory itself, and its model-independent way to test the gravity theory. You can directly check what is the allowed gauge degree of freedom for gravity theory by just looking at the correlation curve of pulsar data. You can also measure the gravity speed or graviton mass by looking at this shape of correlation curve. You can measure clock signal. You can measure position error. That will actually also have profound astrophysical implications. You can measure the clock. You can measure how the international clock ensemble behaves, whether the international atomic clock is drifting towards particular values. And we checked, indeed, the international clock ensemble clock is not that stable at the early time, 1990s, and stabilized after 2000. And there is a post-correction called BIPM time, and that's stable. So by using the pulsar data, we can show that the post-correction of BIPM is actually more accurate than the everyday you use TAI. And you can measure the solar system properties, because measuring the pulsar signal depends on the Earth's position, so you can figure out how the dynamics of the solar system really behaves. You can check whether there is unknown mass in the solar system by looking at the pulsar data. Here is the upper bounds. That's 1 to 3 sigma upper bounds. And within, say, a couple of AU radii close to the sun, we know that there is no planets, a dwarf, rock, or small black hole, cosmic string loop, or alien spaceship heavier than 10 to the power of 20 kilogram. Otherwise, we will see the signal inside our pulse timing data. We can measure the acceleration of our galaxy inside the Milky Way. And that's that's the best thing we can do one day once we have good enough data. And that time we'll be able to see how the sun is being attracted by the nearest stars. In general, different gravitational wave detectors cover different bands. And the pulse-timing array covers this low frequency band called nanohertz band. And the frequency, the period of the gravitational wave is roughly on time scale of years. And because of this, from about 2000, various of international pulse-timing array collaboration are formed aiming at gravitational wave detection. The first form, the pulse-timing array, is actually the PPTA about 2004. And then nanograph and the EPTA. EPTA have some historical data, so that's why their data trace back to 1996. Indian PTA and South African PTA are emerging PTAs. CPTA formed actually very late at 2019, once the FAST telescope is running. So how CPTA is doing? CPTA has actually some long history. Back in 2003, Dr. Wang Shouguan here, he proposed to build a 50-meter telescope in Miyun, close to Beijing, to initialize the Chinese pulse-timing array experiments. The telescope is built, everything is found, goes smoothly, but later astronomer doesn't have a chance to use that telescope. The telescope is being used for other purpose. 2009, we tried to implement the pulse-timing array proposal in the FAST project, and that became one of the key drive to build the FAST telescope. And 2010, we started to use a small dish in Kunming, 40-meter radio telescope, to understand how to do high-precision pulse-timing. And that time, we tried a lot of things, and we get microseconds timing precision. It's good. We get all the experience and technology ready, but compared to the other data on the international market, the timing precision is still very bad. So April 2019, FAST started to experiments pulse-timing observation, and the second day after we do the experiment and process the data, exactly the second day, we formed the second Chinese pulse-timing array collaboration meeting, and we agreed to finally form the CPTA collaboration. We want to use FAST to do pulse-timing experiments and to catch up the gravitational wave. We put this figure in the proposal that's basically tell you how much signal-to-noise ratio of gravitational wave detection you will have for how long observation you took. In 2020, the proposal gets granted, and we start observing. So how FAST helps here? Those telescopes, the size of the telescope here are drawing in scale. So that's FAST, that's Arecibo. Equivalently, the FAST collecting area is equivalent to the summation of the rest of the telescope observing pulsar of the planet. So with a better signal-to-noise ratio, you can do better calibration. And if you have any systematics, it's easy to spot and mitigate. And it's also easy to spot mistake and track down the problems. With this big telescope, things move really smooth. 2003, we performed the first release of CPTA, and that's a data coverage across, say, 3 years time scale. Those are the pulsars we see. Basically, those are the pulsars in the field of FAST we can see, and we just observe them. And if you look at the timing precision of those pulsars, basically the timing precision is the fluctuation of these data sets. You can see for a significant fraction of pulsars, we achieved 100 nanoseconds timing precision. Some of the pulsars we can achieve tenths of nanoseconds precision. If you remember a couple of pages ago, the detection sensitivity, here the detectable regime would be 100 nanoseconds pulse timing precision for 20 pulsar observed for 5 years. And for FAST data, we start to match that criterion. And even better, we have 56 pulsars are doing that instead of 20. So overall, the data quality compared to the international data sets, the data precision is improved by a factor of 4 to 50. And for each pulsar, I just plot the RMS error here on this plot. And after that, we do the parameter estimation. And 2023, 4 different teams, European pulse-time array, Parkes pulse-time array in Australia, and nanograph in North America. We publish a paper together at the same time. We get roughly the same amplitude of gravitational wave from different data sets. Different people using different telescope, analyzing different data sets, get roughly the same amplitude of gravitational wave. We didn't contact each other before we see the final results, so the agreement is astonishingly well. So for the CPT data sets, because the data length is still very short, we didn't catch up the spectral index of the stochastic background very well. And for longer data sets like EPTA or nanograph, they can actually measure the spectral index to some good precision. There is some indication that those gravitational waves are not purely generated from supermassive black hole binaries. There might be extra thing happens, like cosmic string or something else. The key thing is whether you can really confirm this is gravitational wave. To do that, you need to check the Helling-Sandans correlation. And the 4 different calibration actually see the correlation curve. That's from EPTA, that's from nanograph, that's from PPTA, that's from CPTA. Using different technique, slightly different technique. But we all see the Helling-Sandans correlation. Well, it's not very high significant. We only get about 4 sigma-ish. But it's an indication that the Helling-Stans curve or Helling-Stans correlation is there, and the signal we see is really gravitational wave of nanohertz band. What will happen in the near future? So on the international view, we'll have a lot of new telescopes. VLA is starting observing pulsars, and SKA is coming up. NGVLA is in the pipeline, and the DSA-20 in America is going to observe pulsar as well. The pilot program of the SKA called Meerkat is already observing pulsar, and their result will be published very soon. In China, we are also building something new. We are going to build 200-meter radio telescope, one in Xinjiang province called QTT 110 meter, and another is called JRT in Yunnan province. It's 120-meter radio telescope. We are building something called fast array. The first phase, we are going to build a 40-meter telescope, 24 of them. And we are trying to upgrade a low-frequency array called 21CMA to observe pulsars. This will help us to not only increase the sensitivity, but also increase the frequency coverage to help us to mitigate the interstellar medium systematics, and also increase the view of sky to have more pulsar being observed in the pole. So that's 110 meter in Xinjiang. It's now in the construction phase. The foundation is already built, and the next year they will start to build up the frame and put the dish on. And for 120-meter telescope, that's an imagination plot. It's not been there yet. The construction green light is already granted. The real construction will start December this year. We will upgrade this low-frequency array. It will have about 9,000 dipoles observing at low frequency. And the fast core array, the 40-meter dish for 24 of them, is already start constructing. All those things will happen in the next couple of years. So by different time, you have different frequency coverage to different sensitivity. That's a future of CPTA. What we expect, we will expect that the pulsar number is nearly doubled, so the sensitivity will have a boost somewhere around 2030. Well, sensitivity is not something very interesting, right? But then we will be able to measure the parameters of the stochastic background of gravitational wave to very high accuracy and start to learn the physics. And we will be able to see the single source If we upgrade the system, we'll be able to see a bunch of single source probably, and we'll be able to see the localized individual supermassive black hole binary system. And if one of those belongs to the cosmic string, then we have the first evidence for the defects of our universe. Well, the conclusion is very simple. The post-time array is important for fundamental physics, particularly for nanohertz gravitational wave. The international efforts will systematically further increase the capability of several different post-time arrays. CPT is upgrading the observing system and get ready to meet the dawn of nanohertz gravitational wave astronomy. Thanks.
Thank you so much, Professor Lee. Please remain on the stage, and could you please proceed to the other side of the stage, Professor Lee? Thank you. Yeah, because we're going to have another exciting sharing section will be panel discussion. Could you please proceed to another side of the stage? The keynote speeches cover groundbreaking topics in quantum physics and cosmology. Themes include quantum simulations of atoms and ions, the unification of matter and information linking light and particles, exploration of learning within the quantum universe, and also recent progress in Chinese pulsar timing array research highlighting significant astrophysical advancements. So now we are going to have a panel discussion. May I invite our moderator, Professor Douglas Nelson Lin Chao. Let's invite our moderator. And our panelists including Professor Huang Xinyuan, Professor Li Kegjia, Professor Wen Xiaogang, Professor Peter Zoller. So I may pass the stage to our moderator. Thank you.
Wow, what an incredible series of lectures, ranging from the smallest aspect of nature to the grandest design of the universe. And there is a connection. Would you like to, Peter, would you like to share your thoughts about the connection of this complexity and how can we make sense of it?
Okay, so we're building quantum computers on one hand, trying to get control of the microscopic. And the way that I sort of see that quantum computers are to some extent quantum sensors. And I see the connection with a big scale, just as what we heard in the last talk. Also that, we are building quantum sensing network, where we might be able to distribute entanglement. We might be able, for example, to have, not only satellites flying, but even on a bigger scale, some gravitational wave detectors. We could have atomic clocks that sense, for example, different aspects of general relativity. And so I would say that the microscopic becomes a tool when we distribute it, when we distribute entanglement in the long range sense, to discover something that happens then on these microscopic scales.
Thank you, Peter. Xiaogang, would you like to share your thoughts as well? How it connects to condense, well, all the different aspects of the 8 wonders, plus your question mark with regard to gravity.
Yeah, we usually think those some interaction, Fermi statistics, like fundamental properties. Now in the quantum age, looks like they could be the emergent phenomena. And this point of view actually may have experimental predictions. For example, one prediction is that our universe may have additional cosmic string if the fermion coming from qubits. If you assume fermion is fundamental, then maybe there's no actual cosmic string. If a fermion is emergent from qubits, there must exist additional cosmic string. And then this pulsar timing measurement probably can detect the gravitational wave from the cosmic stream. So all this microscopic quantum point of view and this very microscopic astrophysics point of view actually somehow have this amazing connections. So I'm very happy to learn that. Yeah.
Professor Robert Huang, could you share some thoughts on how AI may enable us to make further advancements on both the quantum world and as well as the global physical world?
Yeah, so in a way, when I talk about the things, learning in the quantum universe, of course, a lot of the talks that I covered was about learning microscopic objects, but we do believe that in the coming future, quantum technology can also play an important role in, say, gravitational wave detection. For example, in the experimental, which is different from this pulsar timing array, but these LIGO experiments, they were already now trying to utilize, say, quantum sensing strategy to enhance their sensitivity in order to better understand these fluctuation in space-time. And in the future, I don't know what the timeline would be like, because I think there's still yet to be explored. It does seem like if we can place, say, a small quantum computer next to these experiments for detecting gravitational wave, there is a possibility that one will be able to hopefully detect fundamental physics that would be invisible to us if we don't put the quantum computer next to it. So many of my collaborators have been exploring that possibilities, and so far we only have proof of principle results, but it does seem like that is there is a potential future in having quantum machines that try to learn from these gravitational wave signals in order to better understand about our universe.
Thank you. One thing that I walked away with an impression from Xiaogang's discussion, that information is reality and particles are, perhaps more virtual. How could gravitational waves from the earliest epoch of the universe, Professor Lee, give us a sense of reality from the information that you have obtained?
So this is a good question. Today, when I listened to the talks before my talk, I'm surprised actually, because Professor Xiaogang Wen asked nearly the same question as we ask at a very large scale. But the basic question is the same: how the matters come from, and how the universe evolved to the current structure. This question, in terms of condensed matter physics, seems to be the emergent phenomenon. And for us, we are observers. We merely see this phenomenon and try to figure out what the process happens inside. We are trying to search for the universe topological defects called cosmic string. That's exactly what Professor Xiaogang Wen has just talked about. And also, surprisingly, I realized that since the universe is a big quantum computer, right? And we are actually just building the readout circuits.
Before I continue further with regard to the panel discussion, perhaps the audience may like to raise some questions that these world-leading experts could provide you with some thoughts. Are there any questions? Yes, please. Back there. Further back. Yes, please.
Good morning, professors. You all so amazing and wonderful. So I'm not from the science background, but I would like to ask something more emotional or intuitive. So, because I have been reading a lot of those synchronicity, 金剛經, quantum physics, quantum entanglements in the past years, because something happens with the synchronicities which drive me to this search for the answers. Why something happens on the same day, and because it's about life and death. Because someone is happy, but someone died at the same date. So simply with these questions is drive me to this journey, and I found a lot of inspirations and answers today. So my question is, do you think that the collective consciousness of human, plants, and animals is part of the quantum computing? Can quantum computing, because it's from artificial intelligence. The value of artificial intelligence is to find out the human intelligence. And also, on top of human intelligence, there's the natural intelligence. So I think the true value for me on quantum computing, all these huge efforts that every scientist is building on, is to elevate the human intelligence. That's the ultimate goal. So how to use these tools to study more about the collective consciousness of human, plants, and animals, everything, even bacteria. So this is my questions. Thank you.
Thank you so much. Would you, Peter, would you like to share some thoughts first, maybe?
I can try to. So, thank you for this very interesting and to some extent deep and also challenging question. I have colleagues, that study, for example, the relation to what extent, the function of the brain or maybe bioscience in general is related to entanglement, and there's some very concrete thoughts about, say, the bird compass, that we have, to what extent quantum effects might, for example, enhance the possibilities in biological systems or in animals or us, to achieve something better, like being more precise, like this quantum compass that we have in birds to sense, for example, magnetic fields. To what extent we can talk about notion of consciousness and so on. This is something much more challenging, and maybe Robert wants to say something along these lines.
Before that, I just want to note that Professor Zoller's home country is Austria. This is the wonderful country that actually contained two great minds, both Schrödinger and, I assume Schrödinger, and Boltzmann and Sigmund Freud. And so maybe the question is combining Sigmund Freud and the concept of quantum information. Xiaogang, would you like to share some thoughts?
Yeah, there are two aspects. One is whether two well-separated human beings can sense each other's emotion states, which probably not. But on the other hand, there's a very interesting question about whether human brain is a classical computer or quantum computer. This is a very, very important question. And one thing I like to say that I think we feel we have free wills. If we want to do something, we'll do it. But this thing is very strange from a physics point of view, because physics, all the phenomena follow equation motion, so they're all determined by your past. So that seems against the free will. So I personally always a puzzle whether free will is something beyond the classical physics or not. But on the other hand, as a condensed matter physics, it's hard to imagine the human brain have a quantum entanglement effect, because the temperature is high and there's a lot of decoherence. But on the hand, I think there's a serious consideration whether the human brain actually can have some quantum entanglement effect. In a sense, maybe some nuclear spin may have maybe really quantum. And so there's a serious research to see whether some nuclear spin entanglement nuclear spin can modify the chemical reaction, and then that may have some effect. But this is really a kind of open question. So we're also wondering what's going on.
Okay, Professor Huang, you have thoughts about interface between human learning, machine learning, and artificial learning, and quantum information?
Yeah, I mean, that's basically what I work on, but I would say that right now I don't think there's an operational way to test consciousness. Like, I've been reading several interesting articles about how one can experimentally test if a human is unconscious or conscious by looking at their brain waves. But I would say right now I don't think there's still a very solid scientific foundation for that. And hence, oftentimes it's quite challenging to combine these subjective experience of consciousness to scientific experiments such as quantum experiments, etc. I do want to say that actually, so I'm currently part of Google Quantum AI, who the leader is Hartmut Navin, and Hartmut he's very excited about this possibility that maybe quantum physics and consciousness can really be related to each other, and we can really answer some of the big open questions in consciousness using ideas from quantum physics. In a way, I think that's how he decided to start this Google team that tried to build quantum computers, so we can now simulate, say, these learning agents within quantum computers and maybe try to test if they're being conscious, how can they learn, and all of these things. But so far, I would say that's still at a very, very early stage. Because especially the subjectiveness, like there's this famous philosophical thought experiment which says, I'm conscious, like I can feel I'm conscious, I can see all of you, but how do I know if you guys are all conscious? Maybe you are all unconscious. So how can I tell that apart? So we need to somehow find a way to answer that. But interestingly, there's these also very famous experiments in quantum information science called Wigner's-Franz paradox, which has this notion of subjectiveness. Like you can have an experimentalist or a person that is looking at another person, and then that person is doing some experiments, and now the person measures certain things, but now I look at that whole system, and they will still just be in a big superposition, and if I try to measure them, I would get entangled in it, and if there's another person that tried to look at this, it would not see that I have this subjective experience of looking at certain experimental outcome. And they were able to formulate a very fascinating paradox that I would say in the quantum foundation, which is a subfield within quantum information science, try to better understand. So there's these recent works by people in ETH Zurich. I know Renato Renner was a very big proponent or like a big scientist exploring that frontier. I don't personally know that much, but it does seem like quantum physics provides these notion of subjective experiences that might be related to consciousness. But I would say right now it's still very unclear.
Thank you. Perhaps a couple more questions. You have a very eager hand. Please.
Thank you.
Turn on.
Yeah. All right. Thank you so much. Thank you all for these amazing presentations, and I really learned a lot from by taking notes and watching the slides and hearing your speeches. So I don't have a science background. I'm now working for a Chinese entrepreneur organization. So I'll ask all of the speakers like a few the questions about how the science will affect the business. Which industries do you believe will be deeply affected by the advancement of the quantum technology and science in the future? So, how would this technology influence the fate of humanity in the future? Thank you so much.
What about quantum communication? And Peter, would you like to share some thoughts?
Yes, I would say that one of the most, sort of close applications where we're already kind of in the middle, I would say at the moment, of all of these quantum physics and technology is, of course, quantum communication. I just want to remind you of the great experiments that are being done, even involving satellites, in China, where we talk about, teleporting quantum states, where we talk about quantum cryptography. And these are things that we're able to do right now. And just, when you apply these things to the security on whatever level, I mean, this has immediate consequences. And I would say that, sort of extending these kind of ideas then, the possibility of quantum communication to networked and also quantum computers that can start to talk to each other in some non-local way. I think all of them, I mean, they offer really completely new possibilities that we're just at the moment starting to explore.
Okay, thank you. Maybe we can ask some more questions. Back there, on the third row, please.
Thank you, Professor, for all wonderful presentations. I have a specific academic question. That is, how can we calculate the amount of information loss in the learning process of quantum systems? And after that, is it possible for the information to increase during the learning process? Thank you.
Okay, maybe that's a question for me. Yeah, so there are many different ways of talking about complexity in learning. There are many different notions. One of the most common one is known as sample complexity, which means how many samples, how many measurements, how many experiments do one need in order to learn. And in various cases, quite surprisingly, we can get a very good handle on that complexity. But in addition to sample complexity, there's also this notion of computational complexity, which try to characterize, if you wanted to learn certain things, how much computational time do you need? And that is oftentimes a much more challenging thing to characterize, because computation is just a much more elusive object. But more recently, by utilizing ideas from quantum cryptography, we were also able to make progress in characterizing computational complexity. So there's sample complexity, there's computational complexity. One could also ask a lot of other things, like how much memory do I need in order to learn certain object, in order to learn to solve certain problems? And all of that have a lot of very fascinating different properties, and they all have different connection to one another. Sometimes one can be very different from the other. For example, the sample complexity might be very small, but actually the computational complexity would be extraordinarily large. So understanding that, I would say also is a very important aspect of this intersection between learning theory and quantum information.
Okay, maybe the last two questions, okay? And maybe someone from the back there. Yeah, you. Don't turn around, right, you. Yeah.
Yeah, actually, I just have a technical question for Xinyuan. So you mentioned that classical algorithm can efficiently simulate quantum systems. So this classical machine learning algorithm, you mean based on the current developed algorithm, or maybe some new algorithm we should develop in the future? And of course, the second related question is that there's also notion of quantum machine learning. So do you think quantum machine learning can also be approximated by certain classical algorithm? Thanks.
Yeah, that's a great question. So the first, classical algorithm cannot simulate quantum system very well. That's also one of the results that I mentioned. What I was talking about was more like these classical machine learning algorithms that can learn from quantum experiments. And the reason that it can suddenly solve problems, quantum problems that classical algorithm cannot, is because in a way it's like inheriting computational power from quantum experiments. And that was one of the reasons why they can solve that. And I would say, in a way, like I guess the first question was, is it something that we can already do now, or we still need to develop it further? I would say a lot of things can already be done now. Like the algorithm that I was talking about, when I say there exists a classical machine learning algorithm, we actually write down the algorithm, and we also tested it numerically, seeing that it can do a lot of wonderful things. So a lot of those can, I would say, can already be applied using current technology. But I do believe that there's going to be further development that would really enhance the power of classical learning algorithm to solve quantum problems. And can quantum machine learning algorithms also be simulated by these classical machine learning algorithms? Some of them, yes. Some of them, actually, that was one of the key message in this Power of Data in Quantum Machine Learning paper that I very briefly mentioned. But one of the results there is that certain quantum machine learning algorithm, even though it's hard to simulate by classical algorithm, when we now use classical machine learning algorithm, it can actually simulate them. So some of them, yes. And that also builds a stage for why we then start to think, are there cases where we can just prove that this quantum machine learning algorithm would just not be simulatable by any classical machine learning algorithms? And that leads to some of the results that I talked about towards the end of the talk. So that's right.
Thank you. One last question. Okay. I'm trying to spot maybe a lady somewhere, but that's okay. Maybe you raise your hand several times, right? So I could just give you that last chance. My apologies that the time is limited because there's a short lunch break. So.
Thank you so much. Thank you, our guests, to give us wonderful talks. My question is about, I'm in physics and math background, so my question is to Dr. Wen Xiaogang. The question is about the cubic oceans to describe the universe. So I saw from your PowerPoint that the model, we have the string, we have the open string and closed string, and we have the string to net interactions to model for the fundamental principles. So my question is that how about boson? Because in your presentation you have the Fermi statistics. My question is about whether how can we do boson statistics so that it will related to the collection of mass and then the long-range massive effect and then the gravity. So my wonder is how about to create the boson statistics from your hypothesis? Thank you.
Yeah, the boson statistic is kind of easy in a sense. Like in the qubits ocean, you say if a qubits O equal to 0, that's a background. There's nothing. The qubits 1 represent a particle, and this qubits 1 can move around. So this qubit is equal to 1, or that qubit is equal to 1. So that's representing this, the 1 representing particle representing, actually that's representing the boson. So this is 1 moving around actually corresponds to boson moving around. So actually without quantum entanglement, we already have a boson, and those bosons are already identical particles. So that's quite impressive because the notion of identical particle is pretty strange from classical point of view. But from the qubits ocean point of view, it's very natural. We can only have identical particle. But however, at the beginning, physicists thought we can only have identical boson. So the qubits ocean cannot simulate a fermion, and also cannot simulate a photon. Photon is a very special boson, you know. And so people struggle that for 100 years, you know, after Maxwell. Maxwell already tried to imagine something which is either produce a light wave, but it's not quite working. And so only recent years, when we study quantum system, quantum entanglement, we find, not only qubits not only can simulate, this quantum simulator of a qubits not only can simulate the boson, but can also simulate the fermion and also simulate the photon, which is gauge boson. You know, Professor Zoller talked about simulate the gauge, lattice gauge theory. It's really simulating the photon. And so more generally, if we can go further, we can even simulate the so-called SU2 gauge theory, the Yang-Mills gauge theory, or some other things. And I also want to say that the qubits not only can simulate Fermi statistics in 2 dimensions, they can also simulate so-called fractional statistics or non-abelian statistics, something not existing in nature, but possible allowed by mathematics. So this more weird thing can also be simulated. So actually, this will be the one of frontier research, either using quantum simulator to simulate or discover something more exotic effect, not in the nature, or maybe you can build synthesize some quantum material, which gave rise to this fractional statistics, non-abelian statistics, and etc. Yeah. So this so entanglement really have a lot of to offer. Thank you.
Thank you so much. I just want to thank our wonderful, inspirational speakers for this morning. And there's a lot of thought-provoking ideas to take home with, and maybe you can chew on it over lunch. And I will hand it over back to our presenter.
Once again, big hands to our panelists and moderator. Really stunning and exciting sharing. Thank you so much. And now may I invite all the guests, please rise. We have video together. Let's stand closer to each other, then we can have the best photo. Okay, now please, let's stand in one line and then have a look to the center, please. Yeah, I know time is limited, and thank you so much for actively asking questions. I believe you all learned so much. Okay, thank you very much. Thank you so much. So this is the finale of this session. We are about to have lunch. So those who register for luncheon, please follow the instruction from our helpers to the venue. We will see you again at 1:30 with different keynote speakers with different insightful topics. See you at 1:30. Thank you.